Welcome to Lecture 1 Introduction to Networking. In this lecture, we'll go through these topics. We'll first identify what's a data communication network, and then we'll go through different network types, protocol layering, and we'll discuss about two protocol models, that is TCP/IP and the OSI model. So, what is data communications? It is the exchange of data between two devices through some sort of transmission medium. This transmission medium, it can be a wire cable. So if for the data communications to happen, the communicating devices should be part of a communication system. The communication system can be made up of hardware and the software. When you need to find out the effectiveness of a data communication system, we can look at four fundamental characteristics. They are delivery, accuracy, timeliness, and jitter. So now we'll go through them one by one. First one is the delivery. So the system must deliver data to the correct destination, and the data must be received by the intended device or the user. Second one is the accuracy. That means the data should be delivered accurately. If the data has been altered, then that is not usable. Third one is the timeliness. The system must deliver data in a timely manner. If they are delivered late, they are useless. So if you consider a video or an audio transmission, a timely delivery means delivering the data as they are produced. And this is also called as a real-time transmission. The fourth characteristic is the jitter. It means the variation in the packet arrival times. So it is the uneven delay in the delivery of audio or video packets. So for example, let's say a video packet are sent every 30 milliseconds. And if some of the packets arrive with a 30 milliseconds delay and others with a 40 milliseconds delay, that means the video will have an uneven quality. So these are the four fundamental characteristics of a data communication system. Now we look at a data communication system, and this data communication system has 5 components. So you will see the figure in the next slide. So main 5 components are the sender, receiver, message, transmission medium, and the protocol. So you can see in this figure, we have the sender on the left, receiver on the right, and they are connected through the medium. We have the message as well as the protocol. Message is the information or the data that needs to be communicated. So the information can be of the form of text, numbers, pictures, audio, and video. The sender, it is a device that sends the data message. So the sender can be a computer, mobile phone, a video camera, and so on. The third component is the receiver. The receiver is a device that receives a message. Again, it can be a computer, mobile phone, or any other end device. Then we have the transmission medium that connects the sender and the receiver. It is a physical path by which the message travels. So this physical path, it can be a twisted pair cable, coaxial cable, fiber optic cable, or even wireless medium. Then we have the final component, that is the protocol. Protocol is a set of rules. So these rules, they will govern the data communication. So it is an agreement between the communicating devices, in this case the sender and the receiver. So without these rules, the two devices cannot communicate with each other. So this is like two people speaking with different languages. Let's say one person is speaking French, and if the other one is speaking only Japanese, then these two cannot communicate. That means the set of rules or the protocol should be agreed upon by the sender and the receiver. Now let's look at the components in more detail. So messages, the information, they come in different forms. They can be text, that is represented as a bit pattern, numbers, images, audio, and video. So as I mentioned, the text, it can be represented as a bit pattern. So bit pattern means it's a sequence of bits like zeros and ones. So for different bit patterns, there are different text symbols. And this set is called a code. We have different coding systems. The most commonly used one is the Unicode. So it uses a 32 bits to represent a symbol or character used in any language in the world. We also have numbers as information. Numbers are also represented by bit patterns, but we do not have a code. However, we can use conversions like binary to decimal and decimal to binary to convert between binary and decimal, and then the numbers can be represented as a bit pattern. Images, when you are sending them, it can be also represented as a bit pattern. So if we, in its simplest form, an image, it is composed of a matrix of pixels. So pixel is a small dot. The number of pixels depends on the resolution. So when an image is divided into pixels, each pixel is assigned a bit pattern. Then we have audio. So audio means the recording or broadcasting of sound or music. So audio is different to text, numbers or images because it is continuous and it is not discrete. So when we use a microphone as I'm using now to change voice or music to an electric signal, we create a continuous signal. So later we'll look into ways of changing sound or music into a digital or an analog signal. We also have video. It is also a recording or a broadcasting, but it is of a picture or a movie. Video can be produced as a continuous entity, or it can be a combination of images. Then it will be a discrete entity. Now we look at data flow between two devices. As you can see from this figure, we have three methods of data flow. They are simplex, half duplex, and full duplex. In simplex, the data flow is unidirectional. It can only flow from one device to the other. So as you can see from this figure, on the left we have a server and on the right we have the computer. So the server can only send information to the monitor. Then we have half duplex. In this case, both the devices can transmit and receive. However, they cannot do that at the same time. So when one device is sending, the other can only receive. One example is walkie-talkies. And then we have the third figure, the full duplex, where both stations can transmit and receive at the same time. So in full duplex, signals going in one direction share the capacity of the link with signals going in the other direction. So one example is the telecommunication network. So in this slide you can see the explanations given. Networks. Network is the interconnection of a set of devices that can communicate. So a device can be a host, like a computer, mobile phone, workstation, and also a device can be a connecting device, like a router that connects the network to other networks. There are certain number of criteria that a network must be able to meet. First one is the performance. In a network, performance can be measured in many ways. One is the transit time, other one is the response time. So transit time is the amount of time required for a message to travel from one device to the other. And response time is the elapsed time between an inquiry and a response. So this performance can depend on different number of factors like the number of users, the type of transmission medium, and also the capabilities of the connected hardware. Second criteria is the reliability. So it is measured by the frequency of failure, the time it takes a link to recover from a failure, and the network's robustness in a catastrophe. Third one is a security. This include the that means the security issues can include protecting data from unauthorized access and also protecting data from damage and development. It can also include implementing policies and procedures for recovery from breaches and data losses. So we need to discuss about some physical structures, and before that we look at some network attributes. First one is a type of connection. So network is connected devices, and these devices can be connected through links. Link is a communication pathway that allows data to be transferred from one device to another. So if we need to communicate between two devices, they must be connected in some way to the same link at the same time. So there are two different types of connections. One is the point-to-point, and other one is the multi-point. So a point-to-point connection will provide a dedicated link between two devices. So the entire capacity of the link is reserved for transmission between those two devices. In the multi-point, or you can even say multi-drop connection, it is one in which more than two devices share a single link. So in this kind of an environment, the capacity of the channel, it is shared. And if several devices can use a link simultaneously, it is a spatially shared connection. And if the users take turns when sharing, it is called a time shared connection. The next term is physical topology. So this means how the network is connected or laid out physically. So two or more devices connect to a link, and two or more links can form a topology. We'll go through different topologies now. In this figure, you can see a mesh topology. In this case, every device has a dedicated point-to-point link to every other device. So dedicated means the link only carries traffic between the two devices it connects. So you can see in this figure, this is a fully connected mesh topology with 5 devices. Then we have the star topology. In this case, each device has a dedicated point-to-point link only to a hub. So in the middle you can see switch or hub. So it is called a central controller. So the devices has a dedicated point-to-point link only to this controller. The devices, they are not directly linked with each other. So unlike the mesh topology, star topology does not allow direct traffic between devices. The controller is the one who acts as an exchange point. Then we have the bus topology. In this case, it is a multi-point network. So we have one long cable and it acts as the backbone, and all the other devices connect to this backbone link. The nodes can be connected to the bus cable using drop lines and taps. Drop line means it is a connection running between the device and the main cable. Tap means it is a connector that either splices into the main cable or punctures the sheathing of a cable to create a contact. Ring topology, as you can see in this figure, in this case each device has a dedicated point-to-point connection with only the 2 devices on either side of it. So not to all the other devices, but only to the devices on either side of it. So a signal is passed along the ring in one direction. So you can see where the name comes from. It kind of has a ring. So each device in the ring has a repeater. The repeater will regenerate the bits and then they will be passed along. Now we'll look at different network types. We have 2 types to discuss: local area network and wide area network. So local area network, it is usually privately owned, and this can be used to connect some hosts in a single office, building or a campus. So each host in a LAN has an address that is uniquely defined the host in the LAN. So you can see in this figure an isolated LAN in the past and today. If the LANs are used in isolation, that is very rare today, they are designed to allow resources to be shared between the hosts. But however, the LANs we come across today, they are connected to each other and also to WANs. So each host in a LAN has an address, or it is a unique address, and a packet sent by a host to another host carries both the source host and the destination host's unique address. Wide area network or WAN, it is an interconnection of devices capable of communication. However, the difference between the LAN we discussed earlier and the WAN is that LAN is normally limited in size. It can be used within a small area like an office, building or a campus. But WAN, it has a wider geographical area. That is why we call it as wide area. It can be within a town, a state, a country or even the world. So LAN interconnects hosts, WAN interconnects connecting devices like switches, routers or modems. So we have 2 different types of WANs today: point-to-point WANs and switched WANs. You can see a point-to-point WAN here. It is a network that connects two communicating devices through a transmission medium. Then we have the switched WAN. As you can see from this figure, switched WAN is a network with more than two ends. This is usually used in the backbone of communication networks. Internetwork. So we discussed about LANs and WANs. However, they are not used in isolation. They are connected to one another. So when we have two or more networks connecting with each other, they make an internetwork, or we can also call it as the internet. So let's say we have an organization and it has two offices, one on the east coast and other on the west coast. So each office has a LAN that allows all people working in the office to communicate with each other. So to make the communication between employees at different offices possible, the management can lease a point-to-point dedicated WAN from a service provider like a telephone company that connects the two LANs. Then the company will have an internetwork. So in this figure, it shows this internetwork. We have the office on the west coast and the east coast, and they are connected with a point-to-point WAN link. So if you look at this figure, it shows another internetwork or internet with several LANs and WANs. And here you can see different WANs. You can see a point-to-point WAN. Also, you can see a switched WAN. So, an internet, it is two or more networks that can communicate with each other. And this internet, when you use it instead of the internetwork, it starts with a lowercase I. And the most notable internetwork is the internet that is with a capital I. And it has thousands of interconnected networks. So this figure shows a conceptual view of the internet with a capital I. So it can have different backbones, provider networks, and customer networks. So you can see on the top level, the backbones, they are large networks and they are owned by communication companies. Then the backbone networks, they are connected through some complex switching systems like peering points. And then at the second level, we have smaller networks and they are called provider networks. They use the services of the backbones for a fee. The provider networks are connected to the backbones and sometimes to other provider networks. The customer networks, they are the networks at the edge of the internet, and they are the ones actually use the services provided by the internet. They pay fees to the provider networks to receive those services. Backbones and provider networks are also called Internet Service Providers or ISPs. The backbones are often referred to as international ISPs. The provider networks are often referred to as national or regional ISPs. When you need to access the internet, we need to be physically connected to an ISP. So the physical connection, it is normally done through a point-to-point WAN, like a telephone network, cable network, or wireless network. So if you are using the telephone networks, that is the most common type of way to connect to the internet. That means it is the devices within our houses or businesses, they are connected to the telephone network. And because the telephone networks, they are already connected themselves to the internet, one option for our houses is to connect to the internet is to change the voice line between the house and the telephone center to a point-to-point WAN. And this can be done through two ways, dial-up service and the DSL service. Then we can connect to the internet through cable networks. Most of the people use cable TV instead of using antennas. The cable companies, they are upgrading their cable networks and connecting to the internet. So if a house or residence or a business can also connect to the internet using this service. We can also use wireless networks. So wireless connectivity is popular today. So a household or a small business can use a combination of wireless and wired connections to access the internet. There's another method of connecting to the internet, that is using a direct connection. So we are not usually using these in our houses or small offices, but a larger organization can itself become the local ISP and connect to the internet. The most important part from this lecture is the protocol layering. So if you can remember, we discussed what is a protocol before. So when we have a data communication network, protocol will define the rules that both the sender and the receiver should follow. So when the communication is simple, we may only need one simple protocol. But if the communication is complex, then we might need to divide the task between different layers. Then if we are dividing it into layers, then we need a protocol at each layer. That is called as protocol layering. We look at two scenarios. So in the first scenario, it is a simple communication and it is only using one layer. Let's look at this figure. So let's say Maria and Anne, they are neighbors. So communication between Maria and Anne takes place in one layer, face to face, and in the same language. And in this simple case, we can see that a set of rules needs to be followed. First, Maria and Anne know that they should greet each other when they meet. Second, they know that they should confine their vocabulary to the level of their friendship. Third, they know that they should refrain from speaking when the other party is speaking. Fourth one is, each party knows that the conversation should be a dialogue, not a monologue. So that means both should have the opportunity to talk about the issue. Fifth is, they should exchange some nice words when they leave. So we can see that the protocol used by Maria and Anne is different from the communication between a professor and a student. So how they greet, how they communicate, how they live is different between Maria and Anne if you compare it to a professor and a student. The communication in the second case is mostly monologue. Professor will talk most of the time unless a student has a question. And in this case, the communication is very formal and limited to the subject being taught. In the second scenario, I'll show the figure first. We'll assume that Anne is offered a higher level position in a company, but needs to move to another branch located in a city far from Maria. The two friends still want to continue their communication and exchange ideas. So they decide to continue their conversations using regular mail, and that is through normal post office. But they don't want their ideas to be revealed to other people. So they kind of agree on an encryption and decryption technique. The sender of the letter encrypts it so that the others, or if someone else look at it, they cannot read. And the receiver of the letter will decrypt the original letter so she can read it. So we'll discuss about encryption and decryption later, but we'll assume that they are using a certain technique to make it harder for an intruder to read. And in this case, we'll assume this takes place in 3 layers. And Anne and Maria each have 3 machines that can perform the task at each layer. So let's start by assuming that Maria sends the first letter to Anne. Maria talks to the machine at the 3rd layer, and she assumes that the machine is Anne and listening to her. The 3rd layer machine listens to what Maria says, and it will create a plain text, a letter in English, which is passed to the 2nd layer machine. The 2nd layer machine takes a plain text, encrypts it, and creates the ciphertext. And then it is passed on to the 1st layer. The 1st layer machine, let us assume it's a robot, takes a ciphertext, puts it in an envelope, adds the sender and receiver, and mails it. And then the mail is taken by the post or mailman from one place to the other. Then at Anne's side, the 1st layer machine picks up the letter from Anne's mailbox, recognizes that the letter is from Maria because it has the sender address. Then machine takes out the ciphertext from the envelope and delivers it to the 2nd layer machine. The 2nd layer machine decrypts the message, and it will create the plain text and passes this plain text message to the 3rd layer machine. The 3rd layer machine takes a plain text and reads it as though Maria is speaking. So the protocol layering, it enables us to provide a complex task into smaller tasks or several simpler tasks. So if we look at this figure, we could have used only one machine to do the job of all 3 machines. However, if Maria and Anne decide that encryption, decryption is done by the machine is not enough to protect their secrecy, they have to change the whole machine. But in this case, since we are using layering, if we need to change the encryption, decryption algorithm, we only need to change one layer. So, and another advantage of protocol layering is that it allows us to separate the services from the implementation. A layer needs to be able to receive a set of services from the lower layer and to give the services to the upper layer. So we don't care about how the layer is implemented. Another advantage of protocol layering, but it cannot be seen from this example, so you will come across that later. Communication does not always use only 2-end systems, and there are some intermediate systems, and those systems, they can only have some layers, not all the layers. And if we did not use protocol layering, we have to make intermediate systems, not a simpler one, but a complex as the end systems. Now we'll discuss principles of protocol layering. We have two principles. First one is that if we want bidirectional communication, we need to make each layer so that it can perform two opposite tasks. For example, the third layer task is to listen and talk. So in one direction it is listening, on the other direction it is talking. The second principle is that we need to follow the second principle that we need to follow in this kind of protocol layering is that the two objects under each layer at both sides should be identical. So for example, the object under the third layer at both sides should be a plain text letter, and the under the second layer at both sides should be a ciphertext letter. So after looking at those two principles, we can think about logical connections between the layers. That means we have layer-to-layer communication. So Maria and Anne can think there's a logical or imaginary connection between each layer, although it is not exactly there. So if we look at this figure, you can see the logical connection between the layers. This means that we have layer-to-layer communication, but it is a logical connection, that means imaginary connection. This connection at each layer can be used to send object created from that layer. So now we know about protocol layering and logical connections. Therefore, we can move on to talk about TCP/IP protocol suite. TCP means Transmission Control Protocol, IP means Internet Protocol. And this is the one we used in Internet today. It's a hierarchical protocol. We have interactive modules and each will provide a specific functionality. So in the TCP/IP protocol suite, we have 5 layers. We'll start from the bottom: physical layer, data link layer, network layer, transport layer, and application layer. We can call the physical layer as layer 1, data link layer as layer 2, network layer as layer 3, transport layer as layer 4, and application layer as layer 5. So to see how layers are used in the TCP/IP protocol suite, we'll use the figure. In this figure, we'll discuss how layers in the TCP/IP protocol are involved in a communication between two hosts. So in this case, this small internet is made up of 3 LAN, each with a link layer switch. We will also assume that the links are connected by one router. And we'll assume that computer A is communicating with computer B, and we have 5 communicating devices in this communication. So we have the source A or computer A, computer B, and then a link layer switch in link 1, the router, the link layer switch in link 2, and the destination host, that is B. So each device has a set of layers depending on the role of the device. The two hosts, computer A and computer B, they are involved in all 5 layers. Oh, they have all the 5 layers, but the intermediate devices like the switch and the router, they only have a certain number of layers, not all 5 layers. The source host, it needs to create a message in the application layer and it will send it down to the stack. So it will go through application, transport, network, data link and physical layer. And it needs to be physically sent to the destination host. The destination host needs to receive the communication at the physical layer and it will deliver it to the 5 layers to the top. So it will go through physical, data link, network, transport and application layer to the destination B. The router in the middle, it has only 3 layers, so there is no transport to application layer in the router as long as it is only used for routing. So, and then we have switches. They only have 2 layers, physical and data link. So in this case, the link layer switch, it is a link with 2 layers, data link and physical protocols. So each switch, it has 2 different connections. However, the connections are in the same link, which uses only one set of protocols. That means, unlike the router, the link layer switch is only used in one data link and one physical layer. That is why in the router you can see 2 separate data links and 2 separate physical links. The switch is only connecting with one link, but router is connecting between 2 links. So you will understand about this figure when we go through this unit, because we'll discuss each layer separately week by week. So today we'll be only looking at the overall figure and a brief description about each layer. So if I again go through this figure, let's say we need to communicate between A and B. So host A needs to send a message to host B. Then between A and B, we have 2 switches and 1 router. Source A has 5 layers. The message will go through application, transport, network, data link and protocol physical layer, and the message will then go through the physical link between the host A and the first switch. In the switch we have only 2 layers, physical and the data link, and it will come down again through data link and physical layer and then goes through the physical link between the switch and the router. Then the router, in this case, in this router we can see 3 layers, physical, data link and network. So the message will go through the layers to the network layer and then will come down again through the data link and physical layer, and then again it will be connecting to the physical link between the router and the next switch, that is link 2 switch. Again it will go up and come down, and then switch is connecting to the destination B with a physical link, and then when the message comes to destination B, it will go through the stack from physical, data link, network, transport, application layer into destination B. So that is the path taken by a message that is going from source A to source B. Now we look at a brief description of each layer. So in this figure, you can see the logical connections. So these are not actual connections, they are imaginary connections. But these connections makes it easier for us to think about the duty of each layer. So in this figure, it shows the duty of the application, transport and network layers, and they are end-to-end. However, the duty of the data link and physical layers, they are hop-to-hop. So hop means it can be from source to the switch, or a hop can be a switch from hop can be from switch to the router. End-to-end means from source A to source B. So another way of thinking about logical connections is to think about the data unit created from each layer. So in the top 3 layers, the data units or packets, they should not be changed by any router or link layer switch. In the bottom 2 layers, the packet created by the host is changed only by the routers and not by the switches. This is shown in this figure. So it shows the identical objects below each layer related to each device. So we can see in the physical layer, object is bits, is in bits, and then in the data link layer, they are frames, and in the network layer, they are datagrams. So we look at each layer separately. Physical layer, it is the layer responsible for carrying individual bits from one link to the other. Physical layer is the lowest level in this protocol. The communication between two devices at the physical layer is still a logical communication because there is another hidden layer, the transmission medium. So that is under the physical layer. Then we have the data link layer. So as we saw, internet is made up of several links, LANs and WANs, and they are connected by routers. So when the next link to travel is determined by the router, the data link layer is responsible for taking the datagram and moving it across the link. Then we have the network layer. It is responsible for creating a connection between the source computer and the destination computer. The communication at the network layer is host to host. Fourth one is the transport layer. The logical connection at the transport layer is end-to-end. Transport layer at the source host gets a message from the application layer, then encapsulates it in a transport layer packet. We can call it a segment or a user datagram. And then it will be sent through the logical connection to the transport layer at the destination host. So the transport layer is responsible for giving services to the application layer. To get a message from an application program running on the source host and deliver it to the corresponding application program on the destination host. The final one is the application layer. This is again a logical connection between the two application layers, and it is end-to-end. So the two application layers exchange messages between each other, thinking there's a connection between the two layers. However, we don't have an actual link or connection between the two physical layers. However, the communication is done through other layers. So communication at the application layer is between two processes. So if we need to communicate, a process sends a request to the other process and will receive a response. The second model we need to discuss is the OSI model. When we speak about the internet, everyone talks about the TCP/IP protocol suite. But it is not the only protocol that is defined. In 1947, ISO, that is International Organization for Standardization, it came up with the OSI model, that is Open Systems Interconnection Model. It was first introduced in the 1970s. So here you need to be careful. ISO is the organization, OSI is the model. So an open system means it is a set of protocols that allows any two different systems to communicate irrespective of their architecture. So the purpose of OSI model is to show how to facilitate communication between two different systems without requiring changes. OSI model is not a protocol, it is a model for understanding and designing a network architecture. So OSI model was intended to be the basis for the creation of the protocols in the OSI stack. OSI model is again a layered framework. It consists of 7 separate layers. So you can see the OSI model here. We have the layer 1, physical layer, layer 2, data link layer, layer 3, network layer, layer 4, transport layer, layer 5, session layer, layer 6, presentation layer, layer 7, application layer. Since we now looked at OSI and also TCP/IP models, we need to compare the two models. In this figure, you can see both the OSI and the TCP/IP model. So when we compare the two models, we can see that two layers, session and presentation, those two layers, they are not there in the TCP/IP protocol suite. So they were not added to the TCP/IP model after the publication of the OSI model. The application layer in the TCP/IP model is considered to be the combination of all those three layers. So application layer in the TCP/IP contains application, presentation and session layers from the OSI model. They mention two reasons. First, TCP/IP has more than one transport layer protocol. Some of the functionalities of the session layer are available in some of the transport layer protocols. The second reason was the application layer is not only one piece of software. Many applications can be developed at this layer. If some of the functionalities mentioned in the session and presentation layers are needed for a particular application, they can be included in the development of that piece of software. So OSI model, it came after the TCP/IP model. So most experts, they were excited and they thought that TCP/IP will be replaced by the OSI model. But it did not happen for several reasons. But we'll only look at three. OSI was completed when TCP/IP was fully in place. So if we are going to change it, that means it will cost a lot. Second, some layers in the OSI model, they were never fully defined. For example, Although the services provided by the presentation and the session layer were listed in the document, the actual protocols were not fully defined. And also the corresponding software was not fully developed. Third, when OSI was implemented by an organization in a different application, it did not show a high enough level of performance to encourage the Internet Authority to switch from the TCP/IP to the OSI model. That is the end of this lecture. See you in the next one. Thank you.